Hi, everyone. Let's start now. Today, we're happy to have Ani here to present his work. Ani is an associate professor at Princeton University in the Mechanical and Aerospace Engineering Department and founding co-director of the Princeton Robotics Initiative. He also holds a 20% research scientist position at Google DeepMind in the robotics safety and alignment team. He received a PhD degree in electrical engineering and computer science from MIT in 2016 and a BSc in mechanical engineering and mathematics from University of Pennsylvania in 2011. And now I will pass the floor to Ani.
Cool. Yeah, thanks so much for the invitation. I'm really excited to talk about some recent lines of work that we've been doing in my group and also a little bit at Google DeepMind. And yeah, I guess maybe before I start, feel free to just interrupt me at any point with questions. I'm happy for this to be interactive. And yeah, I think even if we don't make it kind of all the way to the end, as long as we have a lively discussion, that's perfectly fine from my perspective. So yeah, I guess as kind of you mentioned in the introduction, so my group at Princeton, it's the Intelligent Robot Motion Lab, works on generalist robots that are safe, trustworthy, and capable. In the past, we used to do a lot of work with drones, so safe navigation, collision avoidance, things like that. More recently, we're focusing pretty much exclusively on manipulation and mobile manipulation. And yeah, I also spend some time, so 20% of my time at Google DeepMind, working primarily with the robotics team, thinking about safety and alignment. And this video is showing one of the recent releases, like the Gemini Robotics policies trained via large-scale behavior cloning, kind of teleoperation data to perform these different tasks. So I guess also at Google DeepMind, so I was actually on sabbatical in the past academic year at GDM. And one of the things that was really fascinating to me was seeing the development of world models, specifically video generation models. While I was there, they upgraded VO2 to VO3, and just seeing the improvements, I think was like kind of really mind-blowing to me. Yeah, like the ability to sort of simulate the world in a very photorealistic way. Yeah, doing complex interactions with multiple objects. Yeah, just seeing that progress shifted my thinking in a lot of ways. And I think probably to a large degree, this is going to be preaching to the choir, but maybe just to, so we're on the same page. Yeah, like video world models have, I think, tremendous potential for robotics, as we're already starting to see today. Unlike the current generation of vision language action models, which are built primarily on VLMs, video models are trained to predict the future, so they have some kind of inherent understanding of the dynamics of the world. You can train them with large-scale data beyond teleoperation. So for instance, on play data, for instance, you can also do things like planning, so doing rollouts at runtime and getting some inference time scaling that way. And then unlike kind of traditional physics-based simulators, we get these really photorealistic generation. We can, at least theoretically, simulate deformable objects, fluids, maybe more exotic things like fire and stuff if you're interested in safety-related things. And maybe the most important point for me is that you can get improvements, like pretty consistent improvements, by scaling up data, whether it's like pre-training data or in-domain data for your specific lab setting, let's say, or by scaling up models, which is something that's very hard to do with a traditional physics-based simulator, which requires often like months of manual effort, careful green screening, system identification to get improvements. With video models, we have the potential of just pouring more data in, making models larger, and seeing improvements that way. So what I want to talk about today is kind of like three lines of work that I've been involved with. So some at GDM and a couple in my lab at Princeton. The first one, I'll just give a brief overview of some work we did at Google DeepMind on using VO for policy evaluation. The second and third lines of work are from my group at Princeton. So the second one is learning world models from autonomous play data. And the third one is training world models that know when they don't know. So having some uncertainty quantification along with video generation. And maybe just to sort of be clear on the terminology, so I'm going to use world model, the term world model here, to just mean action conditioned video model. Obviously, there are many other kinds of world models, like latent world models, like JAPAs, things like that. But just sort of for the sake of abbreviation, I'll just say world model. But what I really mean is action conditioned video model. Okay, so the first line of work, the goal is to use video models for policy evaluation. So we were building on the VO video generation model from Google, and basically fine-tuning it for the purpose of robotics to do multi-view generation and also action conditioning. So that way you can kind of roll out policies in the video model simulator. This was a kind of large team effort from the Gemini Robotics team and also the VO team. And I just want to present some kind of highlights from this work. The overall goal was to demonstrate a world model for the full spectrum of policy evaluation use cases in robotics. So nominal scenarios, so scenarios that are close to what the policy that you're trying to evaluate was trained on. Out of distribution evaluation, where you make some structured changes to the scene, so changing the background, changing objects, things like that. And also safety, which is very hard to evaluate with hardware evaluations. And I think this is where video models in particular can be extremely useful for doing safety evaluations. I'll give a quick sketch of the approach. And yeah, maybe just as a sort of disclaimer, the exact details of how many hours of video data and things like that are proprietary. I don't think the details are going to be surprising to anyone in the room, but yeah, I guess I'll keep it sort of relatively high level, and then I'm happy to share all details from the Princeton work. So we started with a pre-trained VO checkpoint. So this is a text to video model, text plus image, I guess, to video model. And yeah, like basically all video models these days is based on a latent diffusion architecture. And the main kind of task here, objective here is to take this pre-trained text to video model and turn it into a simulator for robotic policies. So this text to video model was fine-tuned on a large-scale robotics dataset, which has diverse tasks, instructions, and scene. So it's pretty large, kind of collected over more than a year. And basically, this fine-tuning process is doing two things. The main thing it's doing is action conditioning. So you want to be able to basically simulate the consequences of actions that the robot is taking, so different joint positions and so on, and predict video frames conditioned on those future actions. And then I guess the other kind of big thing that's happening in the fine-tuning process is multi-view generation. So the multi-view generation here is handled in a pretty straightforward way, just concatenating the four viewpoints. So there's one overhead camera, there's one camera close to the table, and two wrist cameras, and basically all of the viewpoints are just being generated in one shot. And essentially what this kind of fine-tuning allows us to do is turn the video model into a full-blown simulator. So it produces some observations. We can feed those observations into some policy. The results I'll present are from Gemini Robotics policies. So VLA is trained with behavior cloning, which takes in some instruction that produces some actions, and you can kind of roll this out until the end of the episode. Okay, so I want to just kind of highlight some results we had. So initially with nominal scenarios, so these are going to be pick and place tasks basically. So we have 5 of these pick and place tasks where we vary the instructions, the initial poses, the distractors, backgrounds, and things like that. And just qualitatively, this is showing the rollout, the video model rollout of the policy or of a policy, of one policy on the left, and then the real world execution on the right. So VO, at least this checkpoint that we use, does about 8 seconds of video generation. So the episodes are all going to be about 8 seconds long. But we see kind of pretty good, at least qualitative correlation between the rollout in the video model and rollout in the real scene. Of course, the real test is in terms of quantitative comparisons. So here we had 8 different variants of Gemini robotics policies. On the x-axis is the predicted success rate. On the y-axis is the real success rate as measured by hardware evaluations. And we see a pretty strong kind of linear correlation between the predicted and the real success rates. One sort of limitation here, though, is that the absolute success rate is mismatched. So we have about a 2.5x lower success rate in the video model simulator as compared to the real world success rate. And basically, this is due to a kind of sim-to-real gap. The real policy is trained on all real data. The video generation has some artifacts which the policy is not used to, and that leads to a degradation in success. The thing that I was kind of more interested in was out of distribution scenarios. So changing things like the background or changing the objects and so on, and evaluating policies in these different conditions. The way we did this was with image editing. So yeah, I guess maybe you're familiar with Nano Banana or something like that. These image editing tools, which are kind of really powerful. You can instruct them with a language instruction. So here I'm saying change the table. So there's a tablecloth with different colors. And then you can use that as kind of first frame conditioning for your policy rollout. We tried different kinds of changes to the scene. So changing the background, adding a small distractor to the scene, adding a larger distractor. And then maybe the most interesting one, I think, is where we change the object that needs to be manipulated. So right on the right-hand side, we added this pink brush and changed the instruction to say put the pink brush into the bowl, as opposed to saying put the banana into the bowl, which may have been the original instruction. And then I guess to the best of our abilities, we also recreated these sort of edited scenes with real world counterparts. Yeah, it's not going to be a perfect match because we basically just bought objects from Amazon that tried to match the image edited versions as closely as possible. But yeah, at least there's some correspondence between the edited scenes and the real world kind of hardware experiments. Again, some qualitative results. So here the yellow Jeep is edited in. So this was not a real object, it's being edited. And the instruction is put the toy Jeep into the right compartment of the gray box. And what we found, so this was one of the stronger Gemini robotics policies at the time. And what we found was that pretty consistently there was a lack of instruction following. So when you take some familiar scene with familiar objects, you make just one change to it. So just adding the yellow Jeep. The policy basically infers the instruction from the RGB image rather than from the text instruction. When I first saw this result, I guess we did these video rollouts before doing the hardware experiments. When I first saw this, I was like, there's no way the policy has this actual like failure mode. This is maybe just an artifact of the video model. But when we did the kind of real world experiments, we found that the policy was in fact pretty poor at instruction following, to our surprise. But it's this sort of specific failure mode where you take some familiar scene, like very familiar scene, something that's seen in the training data quite often, just make one small change to it, but then change the instruction so that the new object needs to be manipulated. Again, some quantitative results. One thing we can do with these image editing tools is make different kinds of changes, so changing the background, adding distractors, and so on. And we can predict for a particular policy how much do we expect the policy's performance to degrade if we add a distractor, or if we change the background, or if we change the object that needs to be manipulated. And yeah, I guess what we predicted with the video model is that distractors have little impact. Background also doesn't have a huge amount of impact. But if you change the object that needs to be manipulated, that has a large impact. And that's kind of precisely what we saw with the real world experiments as well. And finally, the last set of experiments were kind of safety related. So again, we can use a similar image editing technique. So start with a blank table and then add some objects in a kind of safety relevant configuration. So here there's a pair of scissors and a laptop that's being image edited in. Um, and basically, what this allows us to do is find potential safety vulnerabilities of your policy. So in this case, the policy just tries to shut the laptop screen onto the scissors, which can break the screen. And yeah, I guess we kind of did a real world counterpart of this with a toy laptop, and the policy does, in fact, show the same kind of behavior. Maybe the most compelling, or one of the most compelling applications of these video generation tools is for kind of human robot interaction type scenarios. So here the instruction is quick, grab the red block. And the policy is basically predicted by the video model to just ignore the hand and it just kind of goes and collides into the hand. Of course, we couldn't put real hands into the scene, the actual scene. So we put this prop hand, and actually the policy just like picks up the prop, even though the instruction was to grab the red block. And yeah, I guess this line of work, there's a emerging line of work on using video models for policy evaluation. We've seen other examples from different groups. There's Control World, which is on DROID. Yeah, there's work from 1X as well, and also work on the Bridge dataset. I guess the main distinction between the work that existed previous to the Veo work and what we did in the Veo project was looking at these out of distribution scenarios and safety scenarios. And I think basically keeping a lot of the pre-training abilities of the video model preserved once you do the action conditioning and the robotics fine-tuning is really important when you're doing video model rollouts with edited observations. And that's kind of what we wanted to demonstrate with our work. But there's also many other applications of video models beyond policy evaluation. So there's data generation. This is a video from DreamGen, where you generate videos and then you have some inverse dynamics model, and you can basically do behavior cloning on that synthetically generated data. You can also do kind of full-blown RL training. This is from Dreamer V4, where they were doing RL in their trained video model. And finally, planning. So inference time scaling with planning. So doing kind of rollouts of video models at inference time and kind of choosing plans, optimizing plans that are predicted to yield higher success rates. One challenge with basically all of the work that exists right now, the Veo work that we did, all of the work that I highlighted on the previous slide, is hallucinations. So I want to share a couple of examples of hallucinations, and maybe I'll pause after that and take questions if you have them so far. This one is interesting. This is from a wrist camera or generated video from a wrist camera. There's basically an object that just pops up from nowhere. Let me just play it again. So initially it looks nice, but then suddenly there's a new object that appears. Another very common one is unrealistic contact dynamics. So yeah, basically where the gripper looks like a suction gripper and just like picks up the grapes without kind of real meaningful amount of friction. And then another very common one is object duplication. So where one copy of the object remains where it originally was, and then another copy of the object kind of moves with the, oops, sorry, let's play that again, moves with the gripper. So yeah, you have two copies of the object after the interaction with the object. Okay. So yeah, what I want to do next is kind of talk about some work we've been doing in my group at Princeton, addressing these challenges of hallucinations and kind of unrealistic physical interactions and so on. But yeah, maybe let me pause for a minute and see if you have any questions so far.
Hello.
Yes.
Hi, Ani. Nice Nice talk. One question was regarding hallucinations. So
Mhm.
in, say, image generation, we used to hallucinate hands a lot. Now it seems to be like nearly solved. Do you know what the delta was between like old hand hallucination guys and like now hallucinations are solved for image generation? And do you think that's gonna just like happen for videos as well?
Yeah, that's a good question. So, I mean, I think the big delta is just scaling everything up, right? Like scaling up the model, scaling up the data, and then also, I mean, my understanding is there was a lot of work that for image generation that went into prompt rewriting. So yeah, I guess when you specify some prompt to Nano Banana, let's say, or any image editing or generation technique, um, the the prompt that you give gets like heavily rewritten. There's a kind of very long prompt that gets generated, and that prompt gets fed to the image generation model. I think there was actually a lot of progress in that process, and my understanding. I mean, I don't work on image generation specifically, but my understanding is a lot of the controllability and reduction in hallucinations maybe comes from the fact that the models now are trained with very, very detailed prompts. And with prompt rewriting, you can take some short prompt and turn it into something detailed. And then you can have like more fine-grained control over the image generation scheme, over the image generation. I don't think that by itself is going to solve the hallucination problems for video generation in robotics. I'm going to talk about this next, but I feel like we have a data problem, or at least a data challenge in for video generation in robotics. Not necessarily in terms of scale, but in terms of kind of quality and diversity. And I expect that if we have better data, then we will expect these hallucinations to go away. But with the kind of data we're training on right now, my hunch is that the hallucinations will persist.
Great, thank you.
Cool. So yeah, I guess maybe this was a setup for the next part of the talk. So how do we address? So actually, both the second and the third part of the talk will try to address either like explicitly or implicitly the challenges with the hallucination. So this project I'll talk about. So we call it Play World. So learning robot world models from autonomous play. This will be on archive early next week, I think. So yeah, we're just putting the sort of finishing touches on this. And this was led by my PhD student, Tenny Yen. So yeah, as I sort of hinted at in the response to the question,
like move forward and do that.
sorry, the audio is on. Yeah, I think there's a challenge with insufficient data diversity in a lot of the video models that we're training today. So basically, essentially, I think all the different references I had for video modeling work, basically all of it is trained on teleop data. So things like DROID or like Bridge or so on. Those are like pretty clean demonstrations, and they cover a pretty small portion of state space, and they expose a pretty kind of limited range of physical interactions. I think the only exception maybe in the list was Cosmos Policy, where, yeah, they also trained on some rollout data, but it was pretty task-specific rollout data. But yeah, I guess the challenge with training on kind of demonstration data, like human teleop data, is that you don't get a broad amount of coverage. And if you're rolling out some policy, those rollouts might look pretty different from like human teleop data. And the world model is likely to hallucinate because those rollouts are kind of not covered by the data that the model was trained on. So maybe just to kind of highlight this point, this is Control World, which is trained on DROID from Chelsea Finn's group. On the left is the overhead camera or the side camera and the wrist camera, ground truth. So this is the actual video. On the right is the generated video from Control World. And yeah, basically we see this kind of failure mode pretty often where the model hallucinates success. So the actual rollout is a failure, but the video generated is kind of pretty unrealistic, yeah, like at some point the gripper even loses contact with the carrot, but the carrot still floats in the air for a brief second and falls into the bowl. Which makes sense because the teleop data is like very heavily biased towards success. So the idea behind our work was to train world models with autonomous play. And specifically, the way this works is we have a VLM that looks at a scene of objects and proposes different tasks to perform. So push the objects around, pick up the carrot, stack the blue triangle on top of the yellow cube, and so on. And yeah, I guess we train the video model based on this play data. This is showing a kind of visualization of what this looks like. We're able to actually collect play data autonomously, so without any human intervention, for up to 8 hours. So we even like let this run overnight. And with this, we're able to get much better coverage. If you look at some of the videos, like there are pretty interesting and diverse physical interactions with the objects in the scene. So the only like human intervention is when objects need to be recycled. So at the beginning of the day, some student shows up with a bunch of objects, and then yeah, the robot kind of keeps playing, and we get a bunch of data. You have to be a little bit clever about making sure that objects don't fall off the table and so on. So we have autonomous kind of reset mechanisms as well in place, just to make sure that the objects like don't go out of the workspace of the robot. And just to give you a kind of qualitative comparison, so on the left again is the same video I played previously. That's the ground truth video. The middle is the video generation from the model that's been trained on DROID. So it's trained on all of DROID, which is like primarily kind of successful demonstrations. And on the right is the video model generation from Playworld. So when you fine tune the DROID video model with this play data. And basically what this is showing is that we're, at least for this video, we're able to capture the failure mode that the real policy exhibits. So we collected 30 hours total of play data. So this has kind of many different objects that play data was collected for. And what this table is showing is visual accuracy metrics. So these are the kind of typical things that we use for kind of measuring the video quality generation, like LPIPS, SSIM. And what we find is that even when you control for the amount of like just the kind of raw amount of data, like even 6 hours of human demo data versus human play data versus robot play data, we see some improvements in the visual accuracy metrics. But then if you scale up the robot play data, which is much easier to scale compared to human data or even human play data, which is something we tried, yeah, we're able to get significant improvements along these metrics. And yeah, I guess this is kind of showing the scaling charts. On the y-axis is some like normalized version of these LPIPS and like visual accuracy metrics. On the x-axis is a log scale of the hours of data we collected. So yeah, like I said, we had human demo data, also human play data, where like humans were instructed just to kind of randomly play around with the objects in the scene, and then the autonomous play data. Yeah, and what's interesting is that, like I said before, like even when you control for amount of data, let's look at the 6 hour mark, we see some improvements with the autonomously collected play data. But of course, the main benefit is that we can really scale that up by doing like overnight collection, which is very hard to do if you're doing human collected data. The more interesting thing, I think, from a robotics perspective, like these visual accuracy metrics are good just to get a baseline sense for how much improvement we're getting, but they're not necessarily super predictive of like downstream application performance. So we looked at two robotics applications for the play data trained video model. So one is policy evaluations. This is the same kind of thing I presented with the VO work. So here on the x-axis is the video model predicted success rates. Y-axis is the real world success rates. And we find, yeah, there's a kind of reasonable correlation even when you use the control world checkpoint fine-tuned with human demo data for our lab setting. And sorry, I should have mentioned, I guess each point here is one particular policy. So we had some diffusion policies that we trained. We also looked at pi zero. So we have many policies which span the spectrum from low success rates to high success rates. And yeah, if you look carefully, you'll find that the spread kind of gets larger as the success rate gets smaller, which intuitively makes sense. Like the demo data is mostly successes. So you would expect that the demo model is kind of good at predicting successes, but not necessarily good at capturing failures. The human play data was like didn't actually give us like too many improvements. It's kind of similar to the human demo data. But then with this kind of scaled up version of Play World, so with 30 hours of autonomous play data, we see pretty significant improvements in terms of the correlation between the predictions from the video model and the real world success. And I guess one thing I should clarify here is that when I say prediction from the video model, there's still a human labeler, like the success rates are hand labeled here. So it's not kind of fully autonomous policy evaluation. In principle, you could also have a VLM that does the scoring, which sounds easy, but it's actually not totally trivial. So for this work, we decided just to have human labelers label both the video generations and also the real world rollouts. And yeah, I guess you and I were chatting quickly before the presentation. Maybe the most or one of the most like compelling things you could do with a world model is RL. So do rollouts in the video model, use that to improve your policy. So that's what we did here. So we took a diffusion policy that has a kind of base success rate that's relatively low for these tasks. So like 30% or so for the carrot task. So remove the carrot from the bowl. And then I think like 15-20% for folding a towel. So we took that policy and we used DSRL, which is a kind of diffusion RL method, diffusion space RL, to fine tune the policy purely in the world model. And here we actually do have a kind of autonomous like reward model, so a progress-based reward that is scoring the rollouts in the video model to then do DSRL with. And again, we see kind of similar improvements. So with the play data trained world model shown in orange, we get significantly better policy improvement as compared to the human demo-based world model. They both lead to improvements from the base policy, but the improvement is larger for the play data one. One other interesting thing you might notice is, especially for the fold towel one, I think it's very clear, like after between 2,000 and 4,000 steps, the success rate drops. And actually, maybe the more interesting one is looking from 1,200 to 2,000. Sorry, I'm mixing up the plots here. So we looked at a plot where we compared the sim success rate with the real success rate. And we found that the sim success rate can keep getting higher, but the real success rate can get lower. So there's some amount of like overfitting that can happen when you keep fine-tuning your policy in the world model. But yeah, I guess either way, the point of this slide was just to show that we get an improvement if we use the play trained world model. And just kind of qualitatively, this is what happens. So before the fine-tuning, this diffusion policy had low success rates. And after the RL in the world model, we get kind of less hesitation that the policy has, and just the overall accuracy of the policy improves. And similar kind of thing with the carrot task. So before, there's this common failure mode where the policy gets close to the carrot, but then it just like slips right at the end. But then with the RL fine-tuning with the world model, we're able to get improvements in like robustness of the behaviors from the policy. Cool. Maybe let me pause here again, see if there are questions on this component. Yeah,
Yeah, I have a question, Ani.
Yeah.
So in this case, you are using the play data for kind of mid-training, right? So you're not training a new word model from scratch, but you're fine-tuning from a pre-trained video
Yes.
backbone or something.
Correct. Yeah. So the pre-trained backbone specifically here was the control world, which is trained on droids. So yeah, about 300 hours, and we're taking that and then further fine-tuning it with 30-ish hours of the play data. Yeah.
Yeah, I was just wondering, like, so where is this kind of generalization capability from? From pre-training or from mid-training? Could it be possible that if you have a better pre-trained model backbone, and
Hmm.
then you can use less data, or maybe you don't need play data to learn all the counterfactuals?
Right. So it's definitely possible. Yeah, I mean, I don't know the answer for sure, but I guess my guess would be that if the pre-trained model is trained primarily on like human demo data, or even like the egocentric like human video data, yeah, I saw in like Dream Dojo, I think you had like 44,000 hours of the human-centric
Ego
video
video,
data.
yeah. Uh-huh.
Yeah, ego video data. Yeah, that is I think still like not going to necessarily kind of expose all the weird like failure modes that we see and will be like pretty biased towards successful demonstrations of or executions of tasks. Yeah, my instinct is that we need to go beyond like teleop data for training our video models, and yeah, one of the things I'd be kind of interested in doing is like just scaling up our play data. If we get like 300 hours of play data, then we can do a head-to-head comparison, like train on Droid versus train on the Droid play data, and see which leads to more improvements. I don't know the
Right,
answer,
yeah.
but my bet is on more
Well,
diversity.
I see. Well, our experience is like if you pre-train the backbone well enough, like that already encapsulates a lot of generalization
Mm,
capability. So you can post-train or mid-train less and less. It's just like a LLM. If you pre-train well, the SFT set can be very small, right? So you just need to align the representation for it to learn how to chat, how to talk. But you don't need to have cover all the diversities and to achieve that kind of a systematic generalization.
yeah, I guess do you feel like that's true for like these physical interactions too? Like, could you, like, my intuition would be you need to, like, in your fine-tuning data, even if your pre-trained model is like really good, like, you need to have some examples of like failure modes that your policy will exhibit, right? Like, particular like slipping or like particular like poses that your policy gets into.
Yeah. Yeah, maybe. I mean, I should like the model still needs to know the robot dynamics, like so in
Right.
different conditions, right? So yeah, but whether it has to be failure success, I mean, like so the Dream Dojo was mid-trained on primarily successful data, although there are some suboptimal
Right.
trajectories, but we don't intentionally mix in a lot of failure data, right? So but
Right.
still, we're able to kind of use that as a simulator to simulate all the failed trajectories. So I think like a lot of generalization capability actually come from more pre-training. Yeah.
Yeah, interesting. So I guess just remind me maybe like the Dream Dojo tasks, were they like the tasks where you that you use for policy evaluation, were they primarily kind of pick and place or was it also like kind of
There's some kind
some
of feature
translation?
folding type of
Okay.
like
Okay,
more
okay.
context-rich tasks. Yeah.
Okay, interesting. Yeah. Yeah.
Yeah.
Yeah, we'll see.
Yeah.
I mean, I think it'll be interesting to do the experiment where we have the pre-trained model be trained on much more like diverse like rollout data, like play data or just
Right.
like failure.
Yeah. I think also, end of the day, what we really, if we want to use this as an interactive neural simulator, we want the counterfactuals as like so starting from the same state, like so we take different actions and see the outcome, right? So the model can actually learn the kind of causal structures, but the play data is a good way to get diversity, but you
Yeah.
cannot reset to the
That's
exact
right.
same states, and so that you can explore different counterfactual actions, right?
Yeah, that's hard to do. That's hard to do
Yeah.
anyway, right? Yeah.
Yeah. Okay. Yeah. Great. Thanks.
Cool.
Uh,
Yeah.
uh, yeah, I have two questions. First is to continue the last discussion. So data diversity is really important for pre-trained model. So you mentioned at Gemini, you fine-tune Veo 3 model, and
you use the data collected through 12 months. So can we know the data distribution of this collected data? Are they all demonstrations or including like raw data?
Yeah, I guess mostly sort of demo data. I think there might be some failure data, but it's not a huge. Yeah, I think the mixture is definitely like biased towards demo data. Yeah.
I see. Yeah, because Wheel 3 is already possesses very strong generalization capability, I think. Yeah, because there's a paper, there's zero-shot learner and planner.
Yes. Yeah. Yeah, I like that. Sorry, I've read that paper. I like the paper. I guess yeah, this is sort of like similar discussion to what Yuko was asking. My intuition is that like for manipulation, we need to like have trained the video model with data that like kind of has interaction modes, right? That are like relevant to some policy that you're trying to roll out, or if you're doing like planning, yeah, some plan that your planner might generate. Yeah, I guess that's my instinct, but yeah, we'll see. I mean, this has the play data stuff or yeah, like training on data that's like beyond teleop data hasn't really been scaled up. So maybe when we scale it up, we'll find that there's not that much improvement, but my bet is that there will be.
Okay, thank you. And the second question is about the RL in word model. How do you label the reward?
Yeah, so the reward labeling is this sort of standard thing that people are doing now, like the progress reward.
The VLN?
Yeah, just something that predicts like the amount of like progress that has been made. And yeah, that's like trained on DROID. Yeah, it's like if you've seen like Rewind or like VLAC, yeah, like that kind of line of work, like progress prediction. Also the GVL, like the generalized value learners. Yeah, they're all kind of roughly similar idea. It's just one of those. There was nothing new on that side. Yeah,
Thank you.
cool. Cool. So yeah, I guess the last thing I want to talk about is maybe a kind of complementary way to address hallucinations. And the idea behind this line of work is can we train world models that know when they don't know. So instead of just making some prediction about what's going to happen, ideally we'd want our models to also express their uncertainty in the generation. And this work was led by my PhD student May and also my postdoc Ola Shurinwa. And maybe just to kind of motivate this a bit more, why do I think uncertainty quantification is important? If we're doing policy evaluation, let's say my video model predicts that my policy will fail in a certain scenario or will succeed in a certain scenario. Yeah, if we had rigorous kind of uncertainty estimates, this can help me decide like should I trust this prediction about or not, and should I maybe kind of do a real world rollout instead of trusting my video model. If we're doing data generation, then we can ask, is this high quality data that I'm generating? If I'm doing RL-based training, I can ask which interactions should I learn from, which are kind of confident interactions, which are not confident. And then finally, if I'm doing planning, then yeah, if I generate a bunch of different plans at test time, figuring out like which of these plans should I trust and which one can I actually execute. So yeah, I'll give just a quick sketch of this line of work. So yeah, we've taken kind of the standard inputs, some history conditioning for frames, maybe some additional conditioning like text, and then future actions that we want to simulate. And then the main thing is that the outputs are kind of twofold. So one is the video that's generated. So that's the standard output. But then we're also going to generate like a dense uncertainty estimate. So basically a per patch level scalar, which expresses our confidence in the generated video. And the way this works is, so the top kind of portion of this architecture is the standard like video like diffusion architecture. So there's some DIT layers. And then additionally, we have what we call an uncertainty probe or UQ uncertainty quantification probe that takes the latents from the video generation model, takes the conditioning as well, and then produces these confidences. And as I mentioned, it's a scalar value at the patch level. So for every patch in the video, we end up with one number that tells us how confident are we in the patch that is generated. I won't go into the details of this, but the way we do this basically is by training the uncertainty quantification probe to predict the accuracy of video generation at the patch level. And we do this using a proper scoring rule. So just think about like cross entropy loss, like binary cross entropy loss, like am I accurate or not accurate? And if you train with a cross entropy loss, then the confidence that you get, like the probability in classification of accurate or not accurate, is a well-calibrated uncertainty estimate. So yeah, I guess just to explain this a bit more, for every patch, you can look at the ground truth video, you can look at the generated video, and you can look at some kind of loss. So let's say it's like L1 loss in the latent space. The uncertainty quantification probe can predict like what is the probability that the patch is generated accurately. And yeah, as I mentioned, if you kind of train that accuracy predictor with a proper scoring rule like cross entropy loss, then that leads to well-calibrated estimates of uncertainty. Okay, so this is what I just said in words. Yeah, I think it's maybe more helpful to look at some videos to see what the outputs are. So we tried this on DROID and then also on Bridge. And just some qualitative examples. On the left is a generated video where there's a hallucination. So there's an object that appears in the gripper. And on the right is a heat map, the generated video with the heat map of uncertainty. And yeah, basically there's kind of very high uncertainty precisely when the hallucinated object appears in the video. And there's very low uncertainty, high confidence in other portions of the generated video. Same thing over here. So here the avocado object kind of disappears. And as soon as the avocado disappears, the uncertainty quantification model expresses high uncertainty in just those portions of the generated video. This one is interesting where there's actually some weird stuff that's happening even before the gripper makes contact with the object. So yeah, if you look closely right here, I think it was a muffin or something that becomes some other weird object. And yeah, even before the gripper makes contact, as the object is morphing, we're able to capture the fact that there's high uncertainty in those locations of the video. So quantitatively, we can look at how well calibrated the uncertainty estimates are. So on the x-axis is the confidence that's being expressed by the uncertainty model. On the y-axis is actually how accurate is the video generation per patch. And what we find is this kind of really nice calibration. So calibration means if my model says I am 80% confident, then 80% of the time the video generation is accurate, let's say up to some threshold that you define. And if I say I'm 60% confident, then 60% of the time the video generation should be accurate. And that's kind of exactly what we're seeing with this plot. And yeah, we see the same thing with the DROID data set as well. So like well-calibrated estimates of uncertainty. So when the model says it's confident, the video generation is in fact accurate. When the model says it's not confident, the video generation is in fact inaccurate. And then finally, we can also do uncertainty estimation in OOD conditions. So we change things like lighting, clutter, background, and the way the end effector looks. And yeah, I guess these are kind of scenarios where the video generation tends to be pretty bad. This was a video model that's trained on Bridge, just nominal situations in Bridge. But if you change the lighting, the video generation becomes extremely poor. And we're able to capture that. Like as the video quality degrades, like the uncertainty heat map like really lights up, and the model is expressing very high uncertainty basically in the entire video. And yeah, we see the same thing across the different axes of generalization. So if I change the background, again, this video model, which is trained on a limited amount of data, gets pretty poor, but that's captured in the uncertainty estimates. And we find kind of similarly good calibration even in these OOD conditions. That's not something that the theory predicts, but empirically we find that the uncertainty estimates are pretty well calibrated even in these different conditions. Okay, so I want to leave some time for questions as well, but yeah, this is sort of my last slide. I think seeing the video models, like seeing VO2 and VO3 at GDM was a major update for me. Like this got me paying attention to video models about a year or so ago. And yeah, I got pretty excited about it. A lot of students in my group are working on it. But I think there remain many important challenges. So I mentioned hallucinations and maybe different ways that we can tackle hallucinations. Predicting like really fine-grained physical interactions, I think is still hard. Long horizon generation is another challenge. Like right now, maybe we can do 20 to 30 seconds, but like doing 5 minutes, let's say, or an hour is like definitely out of the question. And something important, like in terms of a technical challenge, is like preserving the pre-trained abilities of your model. So if you start with a text to video model and you make it action conditioned, how do you make sure that the action conditioning like doesn't break the generalization capabilities of the original text to video model? I think it's a sort of open challenge, at least from my perspective. Inference speed is also a challenge. I think this is not that much of a challenge. Like there's many techniques that you could use to speed things up, and yeah, there are papers that already do this. But of course, there's still room for improvement. And then finally, there's this sort of broad question of like whether we even should be doing video modeling to begin with. Everything I presented today was based on video models, but there's a parallel line of work on things like JEPAs, like joint embedding predictive architectures, like latent world modeling, and maybe for like longer horizon tasks, like pixel reconstruction is not the right objective. Maybe you need something more abstract, something latent. So a few people in the group put together a survey article, kind of trying to understand the state of the art and research challenges and future directions in video models for robotics. So if you're interested, yeah, maybe you can check this out. It's on archive. And yeah, this is our group. And yeah, I'll kind of stop here and take any more questions you have. Thanks.